kilograms of water. And it was going to go, thank you, for a liquid to a solid. It was freezing. I gave you some values, one of which was the molar enthalpy of melting, which was 6.01 kilojoules per mole. So therefore, to freeze it, the molar enthalpy of freezing was negative 6.01 kilojoules per mole. So all you had to do to figure out the enthalpy change to solidify 1,000 kilograms is to figure out how many moles that is. So you have that many kilograms, so you have that many grams. Your molar mass is grams per mole. So one, two, three. Okay. So 1 million grams of water are frozen. You should have a large number. You end up with something like 55,000 moles of water. So 55,000 moles times negative 6.01 kilojoule per mole. So you get a large number. So then you had to do an enthalpy diagram. So it was just, you had to label it. That's it. You take your thermochemical equation and you put it in a graph form. So if I ask you to calculate a delta H value, that's the only time you use that delta H. You use your molar enthalpy to help you get an energy level diagram and a thermochemical equation. So the elements are nitrogen gas, hydrogen gas, and chlorine gas. And then you balance it so that you get the subscripts on the right. You can't change what's on the right-hand side of the arrow. So you have to put a half in front of N2, a half in front of chlorine, and a 2 in front of hydrogen. It tells you that the molar enthalpy of formation for ammonium chloride is 314.6 kilojoules per mole, and it's exothermic. So the energy goes on the right-hand side. There's your thermochemical equation for the formation of ammonium chloride. But now it wants the amount of energy to produce hydrogen gas from the decomposition. So decomposition means we're going to flip it. So now, NH4Cl plus 314.6 kilojoules will produce half a mole of N2, 2 moles of H2, and a half a mole of Cl2. You need to find the molar enthalpy with respect to H2. So, 314.6 kilojoules are needed to produce 2 moles of H2. So, 157.3 kilojoules are needed for every 1 mole of H2. Take that number and multiply it by the number of moles of hydrogen gas you form. You'll figure out how much energy you needed. So this is a delta H for H2. So, figure out the enthalpy change per mole of substance. Figure out how many moles you have, and you figured out how much energy you need. What would you end up doing then if it asked you for chlorine? If I said I want to make 5 grams of chlorine gas, what would you do to this equation to figure out for chlorine gas?
Would you divide the 314.6 by a half and then get their
Yeah, that'll give you a molar enthalpy for chlorine. So you divide by a half, so you would actually need 600 kilojoules to produce 1 mole of chlorine. You have to get it in terms of moles. 1 mole, because that's a molar enthalpy, and then you multiply it by the number of moles. So 314 will produce half a mole, so you'll need twice as much energy to produce 1 mole. It's 20% ethane. And it's 80% butane by mass. If it's a 10-gram sample, that means 2 grams are ethane, 8 grams are butane. You've got a molar mass, so if you divide that by the molar mass, you'll get the number of moles. Pretty sure everybody who tried this question got that answer. Please don't leave it as a fraction. So that one is 0.066489 moles, and this one 0.137599 moles. So we know how many moles of gas for each substance. Now, we're burning this. This is a fuel. Bless you. So you need a balanced chemical equation. For these. And I gave you,
I remember.
let's do these one at a time. You've got ethane. So delta H is equal to the sum of the enthalpies of formation of your products minus the sum of the enthalpy change of your reactants. So we're using this formula, which is the only thing other than writing a formation of reaction question that you've done with them. So we need, for ethane, 2 moles times the molar enthalpy of formation of CO2, which is negative 393.5. Plus 3 times the molar enthalpy of formation of water. So that's our products. Now our reactants. 2 times the enthalpy of formation of 1 mole times the molar enthalpy of formation of ethane. And 7/2 moles times 0 for our reactants. So now repeat for butane.
So we just like, you just add them up after?
Yeah.
So it's like that easy?
So now, take your molar enthalpies of combustion, multiply them by the moles that you actually had. And that will determine how much energy is released for that amount of fuel. So, if we do ethane, we had 0.066489 moles, and our molar enthalpy was negative 1560.6 kilojoules per mole. For butane, 137599 times negative 2877.4. You figured out how much energy is released for 8 grams of butane and for 2 grams of ethane. If you add those two numbers up, you should have 501 kilojoules. Yeah. which is why I want to take another look at your numbers. I think I know what you did now, which wasn't how you were supposed to do it, but I might be able to give you marks. But you hurt my head. What the? Okay, so negative. Okay, so here we go, negative 501. We know that 120 kilojoules are absorbed, but 501 kilojoules were released. So it's 24% efficient.